Here I've made a quick animation to show how fast that beam falls down in a free fall from the altitude of 1000 meters, and here we assume no other forces. For example, we neglect the air resistance on the Earth. We also neglect the fact that the G itself changes with altitude. For 1000 meters it's negligible. You can see that even though the beam's mass is the same, the gravitational pull, the G value, it's different on different celestial bodies, and that makes quite a difference. The derivation of the equations governing this freefall motion is very straightforward. If we only consider the vertical direction, then you know that the velocity in the y direction, that's the change of vertical position with respect to time. And also acceleration in the y direction, that's the change of the vertical velocity with respect to time. Since we only have the force of gravity, then acceleration, it's actually your g, depending on the celestial body. On each celestial body it's different. And then you can write that g equals the change of vertical velocity with respect to time. Or you can also write dvy equals g times dt. And by the way, the convention is that the velocity and the acceleration up, that would be positive, and then the velocity and the acceleration down, that would be negative. And so what we can do, we can take this equation, dvy equals g dt, and we can integrate it. Since we assume that this g here is constant, we can bring g out of the integral sign. So you will have the integral of dvy equals g times, and then the integral of dt. And so we're going to integrate it from the initial time equals 0 seconds till the final time equals, and then the variable t. And we assume that the beam is at rest at the beginning. So at time equals 0 seconds, your initial y velocity, that's 0 meters per second. And then your final y velocity, we're just going to leave it like a variable. And so therefore what we have is this. On this side, you will have vy, and then here you will have 0, and here you will have vy, and then you will have g times, and then you will have t here, and these are the integral boundaries. And so here on the left side, you will have vy minus 0, and then on the other side you will have g t minus 0, and so your final answer, it will be vy equals g times t. That's the velocity function in the y direction. Since in our convention, positive y is up and negative y is down, since this g acceleration is down, it's going to be negative. So for example, on the Earth, g equals minus 9.81 meters per second squared. And that means that the velocity function on the Earth, it would be minus 9.81 times t. And the same logic applies to Mars, Moon, and the Sun. You will simply have different negative g values. And now, from this formula here, you can see that vy equals dy over dt. You can rewrite it like this. dy equals vy over dt. So now what we're trying to do, we're trying to get a function for the position values. First, what we did, we used acceleration in order to get a function for the velocity values, and now we're going to use that velocity function in order to get a function for our position values. And so this vy, that's this one. That's g times t. So you can rewrite it like this. dy equals g times t dt. And again, we're going to apply integration here. And since this g is constant, at least in our assumptions, because even though the altitude changes by 1,000 meters, then during those 1,000 meters, there is such a tiny change that this g variable undergoes that it's simply negligible. And so we assume that it's constant, and so that means that we can put our integral sign here and leave g out of it. Thus, what we can do, we can determine our integral bounds. Again, we integrate from time initial, which is 0 seconds, up until time final, which is time. We keep it as a variable. We could have put a concrete number here, but we don't want that. We want to have a function as a function of time. So we need to have an open variable in our function, and therefore, for this upper bound, we're just going to keep it as a variable. And so on this side, when time equals 0 seconds, your altitude, your initial y, it's 1,000 meters, and your final y, again, we're going to keep it as a variable. And so we have y here, these are the bounds, and then if I take the integral of this thing, then I will have g over 2, then time squared, and then for the bounds I have 0 and t. And so all that, it will give me y minus 1,000 on one side, and then g over 2 times t squared minus 0, like this. And so ultimately, I will have y equals, and then this 1,000, it will go to the other side. So 1,000 plus 1/2 times g times t squared. And so that's a function for the position values. Here for g, you can simply put the gravitational acceleration for the Earth, Mars, Moon, or the Sun. Since your g is negative, then you can see that as your time increases, your y becomes smaller and smaller with time. So let's say for the Earth, you would have y Earth equals 1,000 and then minus 1/2 times 9.81, which is this g, and you have minus here because this g is negative, and then all that times time squared. And so your beam starts falling from 1,000 meters, and as your time becomes bigger, your ye, your vertical position value, on the Earth decreases. That's why the beam falls down. Anyway, these are called kinematics equations, and in my dynamics courses, I will cover them more extensively. And now, in the next video, I will give you one more exercise so that you could practice unit conversions a bit more. Thank you very much. Welcome back. I have one more exercise for you in order to practice unit conversions. Now we'll focus more on the units for rotations. Imagine that you have a wind turbine, and let's imagine that it rotates at an angular speed 15 RPMs, rounds per minute, and rotation is counterclockwise, so in this direction, against the clock. That's why we call it counterclockwise. The symbol omega is usually used for angular velocities, and then this small I here, that's initial. So at the very beginning, the turbine is rotating at 15 RPM. RPM means rounds per minute. So 15 RPM counterclockwise, it means that in 1 minute, the wind turbine blades will make 15 full rotations counterclockwise. So essentially, in 1 minute, the blades will rotate 15 times 360 degrees. That's what RPM means. Let's now say that due to changes in wind, there has been change in rotational velocity or angular velocity. And this change is, let's call it delta omega 1. The first change, it's 30 degrees per second clockwise. Clockwise means that you're rotating with the clock, so like this. in this way. So that's the change in rotational speed, 30 degrees per second. Not RPMs anymore, but degrees per second, so different units. First of all, the turbine rotates at 15 RPMs counterclockwise, and then the angular velocity changes by 30 degrees per second in the clockwise direction. And then after some time, it changes again. Only this time, this changes, let's call it delta omega 2, it's 216,000 degrees per hour counterclockwise. So this is your second change. Now your unit is degrees per hour. And now this change is in the counterclockwise direction. And so the first question is, what's the final rotational speed, or omega f, of the turbine in radians per second after these two changes? So your initial rotational velocity is 15 RPMs in counterclockwise direction. Then the first change is 30 degrees per second clockwise. The second change is 216,000 degrees per hour counterclockwise. And what's the final rotational speed of the turbine in radians per second? That's your first question. The second question is the following. Let's assume that each blade is 60 meters long. So this is 60 meters long, this is 60 meters long, and this is 60 meters long. And so considering that information, once you have found your final angular velocity, omega f, in radians per second, what is the tangential velocity at the tip of that turbine blade in kilometers per hour when this turbine rotates at omega f, at this final rotational speed in radians per second? So this tip here, it will either have a velocity in this direction or in this direction, depending on this omega f direction. And you have to calculate this tip velocity, and you have to express it in kilometers per hour. In general, when something rotates at omega radians per second, like this, and you have the arm length, let's call it r, and you measure it in meters, then this tangential tip velocity, it can be very easily calculated like this. V equals omega times r. That's how you calculate the tip velocity. And so, what's the tangential velocity of the tip, or let's call it v, when you know that r equals 60 meters, which is what you have here, and you have your omega f. And now this v, it needs to be expressed in kilometers per hour. So good luck, try it yourself first, and then let's talk about it in the next video. Thank you very much. Welcome back. So let's now solve this wind turbine exercise. The initial rotation speed is 15 RPMs counterclockwise. That's the initial angular velocity of the wind turbine. Then it changes by 30 degrees per second clockwise. And then it changes by 216,000 degrees per hour counterclockwise. And we need to find the final angular velocity, or the final rotational speed, in radians per second. That was our first question. And then, once we have that, then we can calculate our tip velocity in this location here in kilometers per hour. But let's start with the first question. The usual convention is that counterclockwise rotation is positive and clockwise rotation is negative. So the final rotation speed can be calculated like this. Omega final, and remember, it had to be in radians per second, it equals 15 RPM, that's omega initial, and remember, it's counterclockwise. That's why you have positive here, a plus sign. Then the first change is minus 30 degrees per second. That's your delta omega 1. And now this one is in clockwise. And that's why you have this minus sign here. And then you have plus 216,000 degrees per hour. And that's your delta omega 2 counterclockwise. That's why you have a plus sign here. However, in this form, it doesn't make sense because each term has different units. So first of all, we need to convert all terms to having one unit only. Since the final answer needs to be in radians per second, then we might as well make all the terms have radians per second. And so we know that if we have one full circle, then in radians, this one full circle, it would be 2 pi radians. And so that means that the first term, omega I, which is this one here, it would be 15 rounds per minute. So this rounds per minute, that's your RPM. You see? Rounds per minute. But now we don't want to have rounds and we don't want to have minutes. We want to have, however, radians and seconds. So we need to cancel out rounds and minutes. And we can do it like this. We can create a ratio here, and I can write here 1 round, and here I will write 2 pi radians. Or if I want to, I can write here 2 rounds and 4 pi radians. Then 2 and 4, they will cancel out, and here I will have 2, and here I will have 1. Or I can write 10 rounds and 20 pi radians. And then this will be 1, and this will be 2. So you see, it doesn't matter. So I will write here 1 round and 2 pi radians. And then I will also create another ratio, and I will write here 1 minute, and here 60 seconds. Or I could have written here 2 minutes, and then 120 seconds, and then I could have simplified them. This would be 1, and this would be 60. And so now I can cancel out the rounds and the minutes, and I'm left with radians and seconds. So I will have 15 times 2 pi over 60, and that will give me pi over 2 radians per second. Of course, pi is approximately 3.14, but let's keep pi here in order to preserve precision. So 15 RPMs counterclockwise, that's pi over 2 radians per second counterclockwise. So the rotation is positive. Then we had delta omega 1, and that's minus 30 degrees per second. It's minus because it's clockwise, and it's a change of the angular velocity. And again, we want to convert it to radians per second. We already have seconds here, but we need to cancel out the degrees and replace it with radians. So again, I will have a ratio here. And so what I also know is that 2 pi radians, it's equivalent to 360 degrees, because 360 degrees is also full rotation. So I will have here 360 degrees, and here 2 pi radians. I can cancel out the degrees, and I will have minus 30 times 2 pi over 360, and that will result in minus pi over 6 radians per second. Or you can also say that it's pi over 6 radians per second clockwise. Remember, this is counterclockwise and this is clockwise. Finally, you have delta omega 2 equals 216,000 degrees per hour. I don't want to have degrees, I don't want to have hours. What I need is radians and seconds. So again, I will have a ratio here. I will say that 360 degrees, it's 2 pi radians. And I will also say that 1 hour has 3,600 seconds. And so just like we canceled out the degrees here, in the same way, we will cancel them out here. And now we will also cancel out the hours. And so you're left with 216,000 times 2 pi over 360 times 3600. And so in the end you will have plus pi over 3 radians per second, or pi over 3 radians per second counterclockwise, like this. And now we can calculate the final angular velocity of the turbine. So omega f equals omega I plus delta omega 1 plus delta omega 2. So that will be pi over 2 radians per second minus pi over 6 radians per second and plus pi over 3 radians per second. And if you add them all up, then you will have 2 pi over 3 radians per second. This number is positive because it ends up being counterclockwise. This number is approximately 2.09 radians per second. But again, it's better to keep this number in this form because then you will not lose the precision. Just keep your pi here, and if you really need to convert this number into something like this, like 2.09, then you can always take this pi and replace it with this number. But unless it's extremely necessary, then it's better if you just keep this pi in this form. So that's the final answer for the first question. This turbine, after all these changes, rotates at 2 pi over 3 radians per second counterclockwise. Welcome back. So now let's do the second one. In the second question, we have to compute the tangential velocity at the tip of the blade in kilometers per hour when the turbine rotates at the final rotational speed. And you already know that the final rotational speed is 2 pi over 3 radians per second. You also know that each blade is 60 meters long. Therefore, the tangential velocity at the tip, it will be omega f times, and then I'm going to put here r, it means radius. In this context, the radius here is 60 meters. So you can imagine that when your turbine is rotating, then this 60 meter here that you see, this is your r, this is your radius, the radius of this circle. And so that means that your v, it's 2 pi over 3 radians per second times 60 meters. So this one is this one, and this one it's this one, and all that, it will give you 40 pi meters per second, or approximately 126 meters per second. But again, if you can, then just leave your pi here in this form. But now you might ask, wait a minute, where did this radians go? Shouldn't it be v equals 40 pi and then radians times meters over second? Shouldn't this be my unit? And shouldn't I do something to get rid of my radians as well? Well, let's see how we get the radians in the first place. Let's write it out in the fundamental SI units. When you have a perfect circle, then this perfect circle has a circumference, let's call it C, and we measure that in meters. The circumference is simply the length of this white line. And this circle also has a diameter, and we measure diameter in meters as well. Both are in meters. And then you know that pi radians equals the circumference that is measured in meters over the diameter that is also measured in meters. So this pi radians, it's just the universal ratio of a circle's circumference and its diameter. And this ratio happens to be the same for all perfect circles. And the value of this ratio is pi radians, or approximately 3.14. Since it's a ratio of a circle's circumference and its diameter, the unit of radians can be written in this form: meters over meters. You can see it here. Pi radians equals C over D, meters over meters. That's the unit. But this meter over meter, you can cancel them out. That really means that radians is actually dimensionless. And so when we go back to our velocity, which is here, then yes, we can write it like this: 40 pi radians times meters over second. However, if we write it down like this, where we include the radians here, then we have to remember that this radians, it's actually meters over meters, and then you also have meters here, it's this one, and so your unit looks like this: meters over meter times meter, and all that over second. But of course I can cancel out these meters here, and so you're only left with meters over second. And that's why I can simply omit radians. It's dimensionless. But of course, this velocity at omega f radians per second, it's expressed in meters per second. But we needed to express this velocity in kilometers per hour. However, it's very easy to make this conversion. Again, we're going to take this 40 pi, which is in meters per second, and we're going to multiply it by a ratio. We know that 1 kilometer, it's 1,000 meters, and we also know that 1 hour is 3,600 seconds. And so now we can cancel out the seconds and also the meters, and you're left with kilometers per hour. And so you will have 40 pi times 3,600 over 1,000. That will give you 144 pi kilometers per hour. That's approximately 452 kilometers per hour. So that's pretty fast. And there you go. This is your answer for question 2. In general, as you can see, it's very easy to convert units using these ratios. You simply cancel out the units that you don't need, and you leave those that you do need. Therefore, I encourage you to always use this method. From my experience, this method reduces the chances that you would make a mistake in unit conversions by a lot. And with that, we have concluded the section of general principles for statics and dynamics. Starting from the next section, we will start focusing on the mechanics problems, either it's statics or dynamics, depending on the course you are enrolled in. Thank you very much.